After getting the idea of about what is meant by a truss element, steps involved in how to solve the problem in a given truss element, I have given in detail all the data. All of you utilize the data, and that will helps you to solve the problem of truss element very easily. So after getting the data, I'll solve the problem on a 2-bar truss shown in figure. This has bar number 1, I'll say element number 1, bar number 2. We have a 2-bar truss element, but we'll not consider this one. This is not a element. Just we have in the same coordinate value, it is not a element, right? 2-bar truss element. Now you can easily understand that why I have defined by using an example of a link and bar. The truss itself is made up of a bar element, but which has interconnectivity with the nodes. When we'll apply the load, there will be having a relative displacement with each other. When we'll have more than one combination of a bar which is not representing in the same axis, is said to be as a truss element. If the bar has in the same axis with the fixed portion, with the next step is said to be as a bar only. When we have a bar is placed with respect to a different axis and which has a relative displacement, is said to be as a truss. We got the idea now. So determine the nodal displacement and stress. We need to find out a nodal displacement at each node. We need to find out the displacement. 3 nodes we have. We need to find out the displacement at each node. We have 2 degrees of freedom at each node. That means Q1, Q2 at node number 1, Q3, Q4, Q5, Q6. 6 numbers of displacement we need to find. So what is that? Q, which is equals to Q1, Q2, Q3, Q4, Q5, Q6. 6 numbers of displacement we need to find, and stress in each element we need to find out. Element number 1 stress, element number 2 stress. We need to find area of cross section 0.01 meter square. For this element, area of cross section is common. A1 is equals to A2 is equals to 0.01 meter square, and Young's modulus E is equals to 210 into 10 to the power of 9 pascals. E is equals to E1 is equals to E2 is equals to 210 into 10 to the power of 9 pascals. That is equals to 10 into 10 to the power of 9 Newton per meter square. 1 Pascal is equals to 1 Newton per meter square. Then 210 into 10 to the power of 9 Pascal is equals to 210 into 10 to the power of 9 Newton per meter square. It's as it is, just Pascal units represented in terms of a Newton per meter square. Force has been applied at this node 100 kilo Newton. Distance between this two node is equals to 1 meter, and from this node to this node 1 meter. The distance what he has given, horizontal distance x direction distance 1 meter, y direction distance 1 meter we have. So how we'll represent this element in terms of a FE model? By considering a 2 degrees of freedom at each node. So here in this node we have a 2 degrees of freedom. In this node we have a 2 degrees of freedom. In this node we have a 2 degrees of freedom in a global coordinate system. Always will start from here. We are giving the node numbering in a positive coordinates to get a correctly representing the coordinate data in a nodal information tabular column. What we have a first step of a truss solutions procedure. So now how we'll represent that one? X and y axis. X and y axis, so this is a positive coordinate system. This is a negative positive, negative positive. This one is a negative negative, and this one is a positive negative, right? So we have all the values should become in a first quadrant. Likewise we need to choose this element. How we need to choose this element? So we have this quadrant. So this one is positive, 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 negative, positive, negative, negative, positive, negative. So in this quadrant, this truss should become. How it should become? All the nodal values. So when I'll take this node at the origin, then only all the nodes will come here in the positive coordinates like this. If I will take this node as a first starting point, instead of this one, how it will get start from here. This two nodal value becomes positive and next value becomes negative. So all nodes are not coming in a same quadrant, it will be moving from one quadrant to the next quadrant. So we need to bring all the nodes value in a positive coordinate, means we need to identify from where I need to start in a given problem. So first I need to identify from where I need to start to get that one. I'll draw a x and y axis from here. So that means it will comes in a positive value, all characteristics will come in a positive. So that means I need to start from here. This is the origin, x is equals to 0, y is equals to 0, and then the node has shifted from this origin to x-axis till here, and then again along y-axis it has been shifted. So what is that x distance? X distance towards this direction 1 meter, it has been shifted. X 2 value, that is equals to 1, and then what is the y2 value? From this direction it has been got shifted, y direction, y2, that is equals to 1. This node is present 1 meters, x2 y2. Similarly we have next bit is this one, this node. So this node is from the origin it has not shifted along x direction value x3, which is equals to 0. Y3, what is the value? Y3, which is away from the origin 1 meter, 0 comma 1. If we know these characteristics, how we are representing this bar element, then it is possible to represent the nodal data in this nodal coordinate data. So now we got the idea how we are representing that all the characteristics in a given problem, and how we are representing the FE model. So in the beginning, the introductory part of the problem is very much important. Now what we have to do, I need to take the given data to solve the problem. First, what is the given data here? Area of cross section 0.01 meter square, Young's modulus 210 into 10 to the power of 9 Pascal, which is equals to 210 into 10 to the power of 9 Newton per meter square. Instead of taking Pascals, I have taken in terms of a Newton meter square. Why? Means the notations we have in terms of a meters. Remove the confusion, I have converted from Pascals to Newton per meter square. What we have to find here, we need to find out a nodal displacement at each member, and also we need to find out the stress in each member in a given problem. Now what is the first step of FEM? We need to create a FE model, then we need to represent all characteristics of the FE model. What are the characteristics of a FE model? We need to define as per the previous procedure. You recall it again. In the beginning of this problem, before starting this problem, I have given the complete details. It has a 3 nodes like this. Is node number 1, node number 2, and node number 3. When I'll join node number 1 to 2, it is said to be as a element number 1. When I'll join node number 2 to 3, I'll say this is element number 2. At node number 1, we have a displacement Q1 due to the application of a force F1. Similarly, at node number 1, along x-axis this is a Q1 and F1. Along y-axis we have a Q2 comma F2, right? So a Q1 F1, Q2 F2. In a bars problem we have only 1 degrees of freedom. Here we have a 2 degrees of freedom. Similarly, we have a node number 2 here. So this node number 2 degrees of freedom I have taken. So that node number 2, just I'll elaborate here to get the clear idea. So node number 2 has a force displacement along x direction Q3. Always will take first x direction, then I will take a vertical y direction. Q3 x direction, Q4 y direction. So due to the application of a force F3 along x direction, and the force along y direction F4, Q4 will be get displaced. We have only the force has been applied in a given truss element vertically downwards at node number 2. So just to that I have represented over here, right? So that is 100 kilonewton. We have applied the load at node number 2 based on our given problem. This force what we are representing here in this direction, this one is a positive force, and this is also a positive force vertical direction, and along x direction this is negative force, and this one is negative force. So in a given condition, the force is applied at node number 2 is negative force. Vertically downward direction 100 kilonewton minus 100 kilonewton. That means F4 is equals to minus 100 kilonewton, that is equals to 10 to the power of 5 newton minus 10 to the power of 5 newton. Why? That force is lies towards the negative axis. After this, node number 3 will represent node number 3 we have a Q5 due to the application of force F5, Q6 due to the application of a force F6. Now we need to write all these characteristics of a FE model. Just I have some statement here. This is a finite element model for a given bar element. See, the Q1 is equals to Q2 is equals to Q5 is equals to Q6 is equals to 0. Where this Q1, Q2, Q5 will comes? Here Q1, Q2 at node number 1. It is fixed along x direction and along y direction. That means the displacement along x and y direction is equals to 0. Similarly, Q5 and 6 is present at node number 3. It is fixed along all direction. All degrees of freedom is fixed. Q5 and Q6 is also equals to 0 due to fixed point. But this Q3 and Q4 is equals to question mark free and force, which are unknown, that is not equals to 0. Now we have based on that element F1, F2, F3, F5, F6 is equals to 0. But here we Q3 is not equals to 0, but here F3 is equals to 0. Why? Force is not given. F1, F2, there is no force at node number 1 along x direction. F1 is equals to 0. Along y direction F2 is equals to 0. I have taken here. Similarly, we have at node number 2, you can see here F3 along x direction F3 is equals to 0. Force has been not given. There is no force. F3 is equals to 0. Similarly, when I will consider F4, F4, there is having a force minus 100 kilonewton, which is not equals to 0. Minus 100 kilonewton is equals to minus 100 into 10 to the power of 3 newton converted in terms of a 10 to the power of 5 newton minus 10 to the power of 5 newton. Again I have this direction of forces, what I have represented there. So that force I have taken negative due to that lies on a negative axis. The force is representing positive axis. With respect to the y direction, representation of a displacement in the same direction, then it is positive. If in opposite direction, then it is negative. So this along x-axis right side it is positive, left side negative, based on the assumptions of a given problem over here. So force is negative with respect to the direction of a representation of a element, right? So then again we need to come to the node number 3. Node number 3, F5 and F6 is equals to 0. Why? There is all degrees of freedom. There is no force has been applied due to the fixed all degrees of freedom along x and y and z direction. It is fixed. There is no force has been applied at 5 and 6. That is equals to 0 due to not applied force on this particular nodes with respect to the position and direction, but only force has been applied at node number 2 vertically downward direction negative axis. Take care of that one concept of this, remember it. After that FE model is over. After getting that FE model, all the nodal data and the elemental data we need to find. Y means elemental stiffness matrix is contains a direction cosine, area of cross section, Young's modulus and length combination, right? So we need to find out the length of the element. See here, we don't know the value of this length of this element. We know this length of this element. How we check out? See, it has been inclined. This element is inclined. The elemental length is given is not parallel to this element. That means it is not a 1 meter. But element number 1 length we need to find out. LE we need to question mark for element number 1. For element number 2, LE for element number 2, that is a L2 parallel to this dimension. That means the length of this element is equals to 1 meter. LE is equals to 1. No need to find. Only we need to find out this length of the element by using a distance equation. LE is equals to under the root of x final minus x initial whole square plus y final minus y initial whole square. By using this equation we can easily get the elemental value, elemental length. Where we have k matrix, I have explained in a procedure that elemental stiffness matrix we have here, this one. So we need to get the area of cross section, we need to get the Young's modulus, we need to get a LE we have found by using the distance equation. But what is this L, what is this M? L means a direction cosine I is equals to, depends upon the x axis, Lij is equals to a value of the x final node and minus value of the initial node divided by LE. We'll get the value of this L for particular element, not a whole truss element, for the particular element. This is an elemental stiffness matrix. M means a depends upon the y axis, then M is equals to final node value of the y minus initial node value of the y direction for that particular element divided by LE is said to be as a M. These are the direction cosine is found by using the coordinate values, coordinate data. By using that coordinate data, we need to find that all the values. That is the reason this data is very much important. Carefully, we need to take this all the data generating this. Both the tabular column will helps you to find out the stiffness matrix. If it is correct, then your stiffness matrix is correct. If it is wrong, your stiffness matrix is goes wrong, right? So it is very much important. Carefully you find these all values LE. So LE means effective length of the element, LM is nothing but a direction cosine. So we know that I have derived that everything, every details I have given while I have derived the stiffness matrix. Now by using a introductory knowledge of the given problem, writing this nodal coordinate data, we know that this stress element node number 1, node number 2, node number 3. I will not concentrate on elements. Now I will consider a only node. Node number 1, what I have stated, which we need to represent in x and y axis. What is the value of this node number 1? It is at an origin 0, 0. The dimension is given here as a 1 meter, and this dimension here is given 1 meter. Now at node number 1 present at an origin, that means x1 y1 value is 0 and 0, node number 1. Now node number 2, it is away from the origin along x-axis as well as along y-axis. So what is the distance along x-axis? It is a parallel to this value 1 meter along x-axis, that is x2 1, and similarly along y-axis it is away from this point to here. So the distance y2 is equals to 1, this 1 meter, right? Y2 x2 y2 is equals to 1 comma 1. We have taken this at node number 2 coordinate data along x and y axis. Similarly at node number 3, node number 3 is not away from the origin with respect to the x axis, it is on the xy axis, that is 0, and then along y axis the distance has maintained, which is equals to 1 meter 1. So this is called it as an a nodal coordinate data, which we are representing with respect to the positions of the node x1 y1, x2 y2, x3 y3. If we have different nodes, another 4, 5, 6 n numbers of nodes, we can take the L coordinate data. Now we got what is meant by a coordinate data. The coordinate data is nothing but a positions of the node is assumed in a global coordinate system with respect to the origin position towards the x and y axis direction positions, and with respect to the node numbering, the nodal data has been entered, that is call it as a coordinate data, is representing as x1 y1, x2 y2, x3 y3, the positions of the node in a global space. After getting this value, now we need to get this elemental data. How many elements we have? We have a two elements, initial node value, final node. We need to concentrate a initial node and final node is very much important. Element number 1 lies between node number 1 and 2, starts from node number 1 and ends at node number 2. So if we get start, it is initial node of the element number 1. That means the value of the element number 1 coordinate value x1 y1 with respect to this position of the node number 1, and similarly for this element number 1 node number 2 ends, where it will get ends, that is x2 y2. And when I'll consider a element number 2 will get starts from node number 2 and ends at node number 3. So now what is the value of x and y for this one? Initial node of element number 2 is what? This one is initial node value, this one is x1 y1 for this element number 2, and then x2 y2 value for this element number 2 is at node number 3. At node number 2 it is x1 y1 for this element, at node number 3 x2 y2 for element number 2. So node, it will get start from node number 2 and ends at node number 3. Instead of taking a 2 2 is this one, we are taking 1 1. Why? Element will get start from node number 2, that is the reason initial node value is x1 and y1. Final node value is nothing but a x2 y2. Final node is 3. Instead of taking 3 3, we have taken a 2. Why? Means the element is lies between the two nodes. The two nodes, initial and final node, we will consider. Initial node means x1 y1, final node means x2 y2. Always we will consider to find out the characteristics of the element, right? So after that elemental length, we need to find elemental length. How we'll find out? We know that concept just now I have explained. So this elemental length value we need to find. First elemental length value, why it has been inclined, no dimension is parallel to that element number 1, but length is parallel to the element number 2, that is 1 millimeter is given in a problem. So L2 which is equals to 1 meter, but L1 which is not equals to 1 meter or any other, that we need to find out. So that means it is lies between node number 1 and 2. Initial node value x1 y1 for this one, and at node number 2 value final value x2 y2. Then we have here this positions in a FE model as similar to that. So I'll consider a node number 1 initial and final node value. So x1 value and y1 value. So x1 y1 value is equals to 0 comma 0 here for a node number 1 of element number 1, this one node number 1 and node number 2, element number 1, to find out the LE. So LE is equals to under the root of x final minus x initial whole square plus of y final minus y initial whole square. So final node is 2. So that means what is the value of the x2 and y2? That is equals to 1 comma 1. So it is away from the x-axis 1 meter and y-axis 1 meter, 1 comma 1. So this is the final value. X final means x2 final, and this is a final, and this one is initial value. So x0 here initial we need to substitute 1 value, final value x final value is 1, we substitute here 1 minus 0 whole square, 1 square plus y final means this one, y initial 0, 1 minus 0 whole square, 1 square is nothing but 1 square is equals to what? Plus 1 plus 1. So we have 1 plus 1 is equals to 2, root of 2 is equals to this value we got. So now we have that same concept here, LE is equals to L1 is equals to 1 minus 0 square minus plus of 1 minus 0 whole square. These values we will take, that is this value is an x1, this value is equals to x2, this value is equals to y1, this value is equals to y2. Now we have substituted that value, we have got this answer. Similarly for element number 2, what is the x1 value, x2 value and x2 and x1 value? What is the x2 element will get start from node number 2 and ends at node number 3. That means we need to take this values, here x1 is equals to 1, here y1 is equals to 1, x2 is equals to 0, y2 is equals to 1. So that means 0 minus 1 whole square plus 1 minus 1 whole square we have here. 0 minus 1 whole square plus 1 minus 1 whole square under the root, that is equals to 1 meter again. Just we have cross verified. After cross verifying also we'll got the same value. No need to find, directly you will take down. Just for the clarification purpose I have calculated. After this we found that elemental data. Then we need to find the direction cosine L and M. This will be depends upon the x value, this will be depends upon the M value. Carefully again we are finding the L value for a element number 1. It is not a length, it is a direction cosine of a given element number 1, and this is a direction cosine for a given element number 1, that is equals to this value. We need to find how to find that L is equals to x final minus x initial divided by LE. So this LE, so when we'll take we'll get this value. Similarly M, that M is equals to y final minus y initial divided by LE. So these equations we have here, x final minus x initial divided by LE. So to find out this value I have considered about element number 1 to find out the direction cosine, that will depends upon the x. So I'll take these values. So this is x1 means x initial, this is x2, that is equals to x final. So then similarly this value is 0, that 0 is equals to y1 is equals to y initial. Similarly this value is equals to y2, that is equals to y final. So we have this one. Now we need to get a L value, means L is equals to x final minus x initial divided by LE. That means L is equals to final means 1 minus initial means 0, 0 whole divided by LE. Just now we have found 1 point some 4 value we have this one 1.412. So we have substituted that values here, and then after calculating that 1 by 1.412 is equals to 0.7082 we have copied here. Then again we need to find out a M value, that M is equals to y final minus y initial divided by LE. Y final is 1 minus this is equals to 0 whole divided 1 to 2, that is 1 minus 0 divided by 1.412, that is equals to same value divided, and then we'll got the same value. So now we need to find out for this L element number 2 and M for element number 2, these values how we'll get here. We need to take this characteristics. This is the initial value, and one is a final value for x and x. So this one is the initial value for y and final value for y. So we'll use this values to find out the L value. This values we will use for to find out the M value, and effective length of the element is equals to 1. So then we have to find out that L that lies between the node number 2 and 3, L23, which is equals to 0 minus 1, 0 minus 1 whole divided by 1. So we have here 0 minus 1 means minus 1 divided by 1 is equals to minus 1. Then again we'll find the value of this. We have here y initial, y final. So m is equals to initial 1 minus 1 divided by le here we have 1 minus 1 divided by 1 is equals to 0. Just we have taken this value here. We have completed this elemental data. This task is completed, done. So only we will use this one, only we will use elemental connection data. That in this also we will use this all the details of the elemental coordinates. After getting that, we have to find, this is the first step of finite element method is over for a truss element. Now elemental stiffness matrix, find it. Elemental stiffness matrix, we know that K is equals to AEE divided by LE. How to remember this? Make it make it that four parts. We have L square, M square. So I'll take for your remembrance how I will remember. You can check out here. I will take L square, M square. So then L square, M square. L square M square, L square M square, minus this one is minus. So what we have, this one I have written like a quadrant: first quadrant, second quadrant, third quadrant, and fourth quadrant. Diagonally you can see this one is a positive, diagonally you can see this one is positive. First and third quadrant is negative, second and fourth quadrant is positive. Remember like this, you can easily remember this matrix. How to remember this matrix? Just now I have given, make it that four parts. So this four part will gives you first quadrant value is negative, second quadrant is positive, third quadrant is negative, and fourth quadrant is positive. Negative, positive, negative, positive. Then we have element number 1. We need to get element number 1 means E is equals to 1. Then A1, E1, L1. This we need to take all the values from the elemental data. See here, LM we need to take A, E, LE. So to get this value of elemental stiffness matrix for element number 1, that element number 1 is this one, lies between 1 and 2. Then we'll go for element number 2. First we'll find this one, right? So to get that, area of cross section is given in a data point 0.01 meter square, and LE. So we need to get this area of cross section. That area of cross section is given data. So see here we have taken a given data, and Young's modulus is a given data. Then length of the element, we have found in a tabular column by using this equation. So that 1.412. And for element number 1 I am considering, for element number 1 L is equals to 0.7082 to 0.7082 m. Both values I'll take here. So you can see that area of cross section 0.01 meter square, L is equals to 1.412, Young's modulus 2 into 10 to the power of 9 Newton per meter square. L is equals to direction cosine 0.07082, m is equals to 0.7082. These three values we have taken from the elemental data. This is the given values. Just all the values you substitute here. Now all the values you will substitute here. You will get that here L square is equals to 0.7082 square. So that is equals to 0.5. See here, similarly m is equals to 0.7082. That means L is equals to m. See here, L square means we have a 0.5, right? So Lm is also becomes a square of this one, that is equals to 0.5. What I have did here, each and every point we have same characteristics. L square is this value 0.5, 5, again this value is a 0.5, and then minus L square. See, concentrate here, I've taken minus. This value is not in a minus value, so directly already we have this minus of minus 0.70825, if for example is there, so this will becomes positive. Again this sign convention will remains as it is. So here, right, followed. So this square for making a only for L, this is already it's there minus sign, but it is not applicable for this one. Minus ml, which is equals to, for example this value is negative, assuming this value is positive, then we have minus of minus 0.7082 into 0.70822, for example. So then this will becomes is equals to 0.5, minus is there, multiply inside, this will be positive. If you have here minus, again this will be remain same. But here while apply the square, minus of L square, that is equals to minus of 0.7082 whole square, or else if it is negative. If now we have the positive, both are positive. For example, if I got that value is negative, means minus of 0.7082, whatever it may be, we'll get the square, means this is also positive, but this will not affect, this is minus, remains minus, right? ML means again this L and M are common, so it is also as similar to square, multiply, that is equals to 0.5. All the values will comes in terms of 0.5, 0.5, 0.5, 0.5, 0.5. I means LM, M square, minus LM, minus M square, minus L square, LM, L square, ML, ML minus M square, ML, M square. This is equals to this value, so that is the reason whole matrix comes in terms of a 0.5. After getting that value of direction cosine in a matrix, then substitute these values in this equation. We know that area of cross section 0.01, Young's modulus, mistakenly have taken 210 into 10 to the power of 9 Newton per meter square. All of you corrected this one. Then the value of length, elemental value, we have found from the table. From this table we have taken this value, that is equals to 1.412. Then calculate this value and I'll multiply 0.5 common, I'll take from here each row. That value is equals to into 0.5. Then this matrix becomes 1 1 minus 1 minus 1 1 1 minus 1 minus 1 minus 1 minus 1 1 1 minus 1 minus 1 1 1 minus 1 minus 1 1 1. So we got this matrix. After getting this matrix, this value into 0.5 is equals to this. Then this value 7.4592 into 10 to the power of 8, 10 to the power of 8 I have taken common. Then this value multiply inside, plus 7.459, all the values you will get in terms of a plus sign minus 7.459 with respect to the sign convention as you have here. So then I have represented this is 1 2 3 4 1 2 3 4. Here you can check out 1 2 3 4 1 2 3 4. So we have these values. So this particular characteristics is with respect to the column node number 1, and these two characteristics is depends upon node number 1. Then these two characteristics, this one and this fully row number 3, which is node number 2 characteristics. Why each node has 2 degrees of freedom. First node has 2 degrees of freedom, Q1 and Q2. Second node has a 2 degrees of freedom, Q3 and Q4. This is lies between a two nodes, which is called as an element number 1. We have the idea. In the previous bars problem, we get a 2 cross 2. Why? It has a only 1 degrees of freedom at each node. Similarly, element number 2, you consider it and substitute the value of area of cross section and Young's modulus. Length of the element we have here, the length of the element in a tabular column we have tabulated, that is equals to 1, and L value is equals to -1, M value is equals to 0. All these values you collect it from the tabular column and substitute here. Here we have L is -1, M is 0, that means L square becomes 1, means L square, that is equals to minus of 1 whole square is equals to 1. We have this one here, it is LM 0. Here it is minus L square is equals to minus of -1 whole square, that is equals to -1. Again we have here -1. Then similarly we have this is LM 0. Then we have this one LM 0, M square 0, then LM 0, and again we have M square is equals to 0, minus M square is equals to 0. Similarly we have these rows. When we substitute these values in this matrix, we'll get this matrix, and the calculated value of this is equals to 21 into 10 to the power of 8, and this matrix will remain same. We have copied, and this 21 has multiplied inside this matrix. We'll get this matrix. After resolving this matrix for an element number 2, give the row name and column name. Element is lies between the two nodes, node number 2 and node number 3, which has a 2 degrees of freedom at each node. We have started the displacement at node number 2 Q3 along x-axis, Q4 along y-axis. Row number 3 and column number row number 1 and column number 1 is given as 3 and 3. It is a first row first column name. Second row second column name as a 4 and 4. Why? That characteristics of a node number 2 along y-axis. Characteristics of the node number 3 along x-axis, we have a Q5. Third row third column is given as a 5 and 5. And then characteristics of a node number 3 along y-axis, Q6, that is equals to fourth row fourth column, right? So this is a given characteristics of an element, which we need to give the row name and column name with respect to the positions of a nodes and the numbers of degrees of freedom chosen in a element. Now after getting that all the values of elemental stiffness matrix, substitute that and bring it in a global stiffness matrix. That global stiffness matrix K is equals to K1 plus K2. We have a 2 element. Similarly I will take this resultant value of the elemental stiffness matrix, element number 1 and element number 2. I'll have added that both the values here, both the same I have taken. So how many numbers of nodes we have? Two nodes, and we have a each node 2 degrees of freedom. We have a 2 cross 2 matrix, right? So for a elemental stiffness matrix, we got this elemental stiffness matrix. Similarly, when I'll consider a whole truss element, in a whole truss element, 3 nodes are there, 3 nodes, and each node has a 2 degrees of freedom. Finally, global stiffness matrix will get 3 into 2, which is equals to 6. 6 cross 6 matrix will get, right? So 6 cross 6 matrix we have here. Just we got the idea in a bar element how to take that stiffness matrix, elemental stiffness matrix, adding in terms of a global stiffness matrix. First row you choose it. Here we have a first row, and but here we don't have any first row. I'll take all these values of first row first column, first row second column, first row third column, first row fourth column. But after this fourth we don't have a fifth column here, and sixth column here, 0 0 we have taken. Similarly, then we need to go for a second row. Second row is here, but we don't have a second row here. We'll take a second row first column value, second row second column value, second row third column value, second row fourth column value, second row fifth column we don't have, that is equals to 0, and sixth column is also equals to 0. We don't have any values here with respect to the second row. Then after the second row third row we have a third row we have in both matrix here. We need to search completely third row first column we have here, but we don't have any first column here. Third row first column, that is equals to minus 7.459. Similarly, third row second column we have minus 7.4592, and then third row third column here, and as well as we have here third row third column we have 7.4592 plus 21, that is equals to 28.4592. for a third row, third column, third row, fourth column, we need to get this value. Third row, fourth column also we have here. Third row, fourth column, 7.4592 plus 0, that means 7.4592, right? Similarly, third row, fifth column we don't have here, but third row, fifth column we have here minus 21, and third row, sixth column we have here 0. Then similarly we need to go with that fourth row. Fourth row we have in this first matrix as well as in a second matrix. Fourth row, first column we have here, but we don't have in here. First row we need to take directly minus of 7.4592, and then fourth row, second column we have this value, and similarly we don't have a fourth row, second column in this matrix, right? So then minus 7.4592 we have taken as it is here. Then fourth row, third column, we need to get this value. Fourth row, third column we have here. Fourth row, third column we have here, this one. Fourth row, third column, this 7.4592 plus 0, that is equals to 7.4592. Fourth row, fourth column, we need to get this one. Fourth row, fourth column here we have, and also in this next matrix, fourth row, fourth column, 7.4592 plus 0 is equals to 7.4592. Fourth row, fourth column we have. Fourth row, fifth column, 0. Fourth row, sixth column 0 we have taken. Similarly, fifth row we need to get, then fifth row we have here, but we don't have any fifth row in this matrix. Fifth row, first column 0 we don't have here. First column, it will get start from 3. Fifth row, first column we don't have. Fifth row, first column 0. Fifth row, second column 0. Fifth row, third column, as we have here 21, minus 21 is that one. Make it this correction, minus 21. And then fifth row, fourth column 0, we have a fifth row, fifth column plus 21. Fifth row, sixth column 0. Sixth row we have here, we don't have any sixth row here. We have this one, sixth row. Sixth row, first column we don't have 0. Sixth row, second column we don't have a 0. Sixth row, third column 0. Fourth column 0. Fifth column and sixth column, all columns we have a 0, 0, 0. All the rows and columns we have assembled. We got that 6 cross 6 matrix. Global displacement vector, it has a lengthy displacement. Instead of taking a vertical vector, we have taken as a horizontal. Instead of taking a column, we are taking it as a row. We have a numbers of displacements or 6 numbers of displacement. That is the reason it becomes a very lengthy row. The space will take larger. That is the reason we have taken this a column in terms of a row, that representing as a transpose matrix to reduce the space. Y means in FEM usually will solve the lengthy problem, so already it will acquire the maximum pages in your booklet of your external examination. We will have a shortage of papers to reduce that. We'll concentrate that also. Okay, so we'll take a q1, q2, q3, q4, q5, q6 transpose matrix, but it is what a same as per the previous method. Q1, q2, q3, q4, q5 and q6 vertically we need to take. Clear? Then we have a q1, q2 is equals to 0, q5, q6 is equals to 0. Why? These forces are fixed. I have given here already the statements with respect to the given diagram, with respect to the given problem positions, right? So now we have this global displacement vector. After this global displacement vector, force vector. Similarly, force vector also have represented in terms of a transpose f1, f2, f6. We have this will take a maximum space of the page to reduce that in terms of a column represented in terms of a row with a transpose, right? So it will remain same. So we have a force only applied at node number 2 here. At this node we have applied the force which is equals to 100 kilonewton downwards, minus we have taken this one minus, and rest of the all forces along x direction. This is a f1, f2 is equals to 0. This is a f3 is equals to 0. f4 minus 100 kilonewton, that is 10 to the power of 5 newton, and then f5 and f6 0. All the forces is equals to 0. Only at node number 2 vertically downwards force has been applied 100 kilonewton. Equilibrium equation for a entire truss element, we found that global stiffness matrix for a a truss element, global displacement vector for a truss element, global force vector for a truss element. Now bring that all three characteristics in terms of equilibrium equation. KQ is equals to F. I have copied that same values here. I got and then I am applying the boundary condition. Now I'll apply the boundary condition. We have a fixed Q1 is equals to Q2 is equals to Q5 is equals to Q6 is equals to 0. Why this are the fixed one? Q1, Q2, Q5, Q6. I'll eliminate the first row, first column with respect to the Q1. I'll eliminate with respect to the Q2, second row, second column, and then Q5, fifth row, fifth column. I'll eliminate with respect to the Q6, sixth row, sixth column. I'll eliminate. Only this value has remains, right? So that 6 cross 6 matrix yields to, after applying the boundary condition, 2 cross 2 matrix. Why rest of the 4 characteristics is fixed? Now I have copied this one, same values here with the 10 to the power of 8. Don't leave it, it's very much important. While you will in your external examination you will get panic, you will leave this value, answer will goes wrong. So you will say that after that, sir, I have did correctly, but all the answers are right, I didn't get the marks. Don't blame on that one. So you carefully take down this one. While I have gone for the valuation, I have seen several time this you will leave. 10 to the power of 8, take down carefully common value, and then here we have a Q3 and Q4.
0 minus 10 to the power of 5. Then convert this matrix in terms of a algebraic equations. Find out the values of Q3 and Q4, or else directly use the calculator. I have explained clearly in a bars problem how to use that calculator by using mod 2 unknowns in a equation. Then enter that coefficient of these values, multiply with this all the values in that equations, like a1 b1 c1, a2 b2 c2 value equals button. You will get a value of a x, that is equals to q3 0.047619 into 10 to the power of minus 3 meters. Y value, which is equals to q4 minus 0.181680 into 10 to the power of minus 3 meters. So we have found that all the displacement, and then he has asked to find out finally a elemental stress in a member. So we have found the displacement at each node, and then we need to find the stress in each element. We have to find out the stress as per the given problem. Stress equation, we have this, I have explained clearly in a steps involved in truss problem and procedure completely. I have given this equation is satisfy which type of problem and how it has been easily we need to remember. I have clearly explained, right? So I have used this equation. Element number 1, if I'll take E is equals to 1 sigma 1 E1 L1 minus L minus M Lm, then Q1 Q2 Q3 and Q4, where I'll take a element number 1 start from node number 1 and ends at node number 2. Here node number 1 has a Q1 and Q2. Here at node number 2 Q3 and Q4. So I have taken Q1 Q2 Q3 and Q4 for a element number 1. Then I have substituted all the values. We know that from the tabular column L, M, we have these values I have substituted, and then I have the length of the element in a tabular column. After calculating, we have tabulated in a elemental data. Then Young's modulus E is equals to 210 into 10 to the power of 5 given. 0 at node number 1 Q1 and Q2 why it is fixed. We have found this Q3 and Q4 value. I have substituted here Q3 and Q4 value. Then you will calculate this matrix. You will get the value of 9.9 into 10 to the power of 6 Newton per meter square. Then similarly element number 2, take down that element number 2, E sigma E becomes sigma 2 E2 L2 minus L minus M Lm. Element will get start from node number 2 and ends at node number 3. So here we have a Q3 and Q4. Q5 and Q6. So that I have taken Q3, Q4, Q5, Q6. Element will get start from node number 2 and ends at node number 3, which will be completely depends upon the element number 2. We have and substitute all those values. It is not remain same. It is completely different for element number 2. Length of the element 1 and direction cosine L is equals to 1, M is equals to 0. We have substitute all those values. So Q3, Q4 we have same values, we have substitute. Q5 and Q6 is 0 due to that node number 3 is fixed. All those values after substituting, calculate that value, will get 38.152 into 10 to the power of 6 Newton per meter square stress induced in a truss element number 2. Thank you for listening my lecture.